Now that you've completed the lab, we're going to take a look at the relationship that hopefully most of you are able to come away with. And that's what's shown here on the screen. Some of you may have written it out as M1 D1 equals M2 times D2. But essentially what we're getting at is the mass multiplied by the distance on one side will be equivalent to the product of the mass multiplied by the distance on the other side to balance everything out, to get everything to be level. Okay? So early in the lab you had a mass positioned on the far end of a meter stick and then moving it to different distances. The closer it is to your hand as you're lifting, the more like the actual weight of that object it will feel like. The further away it is, now you have to do additional work to not only lift it, but also to rotate it. This is the concept of torque that we're getting at. So that's what we're going to take a look at for the next few minutes. So torque is a force acting at a distance from a pivot point. The key for that force is it's perpendicular to the lever arm. Okay. In the case of what we were doing in the lab, the lever arm was the meter stick with the ability to rotate. So this Greek letter here is called tau. That is torque. And it's measured in Newton meters. Our F is force, and R, or sometimes just D, that is our distance. Force will always be measured in newtons. Distance will most of the time be measured in meters, although sometimes can be in centimeters. So when we look at these three examples of different wrenches, if you're tightening or loosening a bolt or a nut, there's a rotation process to make it happen. When you look at all three of these, this bottom one right here is going to be the one that would be the easiest to actually rotate, mainly because the distance is the greatest. You don't necessarily have to apply as much force to get the same amount of torque compared to the others. And if the force is indeed perpendicular to the lever arm, like is shown, that again makes it that much easier to do. Now, when we talk about a force perpendicular to a lever arm, we're always going to have a result of rotation. So, if we apply a force directly through the center of gravity of an object, this causes linear acceleration, or motion simply in a straight line. So if we hit a football right through the center of gravity, the football is not going to topple end over end, it's just going to simply move in a straight line. However, if we have a force that is applied away from the center of gravity, it will always cause rotation. So in the case of a football, if we kick it low, below the center of gravity, we're going to get this end over end motion of the football, much like you would see on a kickoff in a football game. Okay. Other examples, turning a doorknob, tightening a nut or a bolt with a wrench, turning faucet handles. There's all kinds of things that would result in a force away from the center of gravity at the pivot point that results in some kind of a rotation. So equilibrium is ultimately where we're trying to get to with the lab in each of the different examples that you went through. So equilibrium is when there is no rotation because the torque in both directions cancel out. CW here is referencing clockwise, and CCW is simply counterclockwise. So we have our torque equation, F1 times R1 equals F2 times R2. There is a variation on it, which is more what you observed in the lab, mass times radius or distance on both sides. You can use this if we're not being asked to figure out the force. If all we're doing is mass, and as long as we're here on Earth, you can do this variation. So either one ultimately will work. Now there are three problems we'll briefly look at here, and it's ones that we will ultimately encounter as we progress. This first one is one mass on each side. One side we have an unknown amount of mass. So here's how we'll set this problem up. We will assume that the distance here between the pivot point and our known mass is going to be 20 centimeters, and the distance to our unknown mass will be 30 centimeters. Our unknown ultimately is going to be M2. So we can very simply rearrange this equation to isolate M2, which will just simply look like this. M2 equals M1 times R1 over R2. The key is going to be, more than anything else, making sure that we've identified which side is which. So I'm setting this up as though this side over here is side number 1, and this side of our pivot point is side number 2. And if that's the case, all I have to do is plug my values in of 550 grams times 20 centimeters and divide that by the distance to our unknown mass, which is 30 centimeters. When we plug those values in, we end up getting 366.6 repeating grams. That mass should be less than the other side because the distance to it is greater than it is on side number 1. The second example is where we now have a total of 3 different objects, ultimately one unknown mass, but we now have one side that has 2 masses and one side with just 1. So when we set this one up, we're going to have 3 different objects. So we'll use 20 centimeters again on this side. On the right hand side, the distance to the known mass will be 10 centimeters, and the distance to the unknown one will be 30 centimeters. Note that this 30 centimeters is all the way from the pivot point, not just from the nearest object. Every single one of these distances is always measured from the pivot point. So the way a problem like this sets up when there are 3 objects is we look at the fulcrum as the middle point of the whole thing. So we split the equation based on what is on one side of the fulcrum and what is on the other. So this problem is going to look something like this. We'll have M1 times D1 equals M2 D2 plus the product of M3 and D3. And we'll again make this left-hand side object 1, our known object on the right, object 2, and our unknown object will be number 3. So again, the mass, number 3, is our only unknown. So when we go through and set this equation up, so as we set this equation up to isolate M3, what we'll ultimately be doing is we'll be taking M2 times D2 and subtracting it over to this side of the equation. And then at the end of it, we will divide both sides by D3 to get M3 all by itself. So the end equation will look something like this. So that leaves our one unknown M3, and then it's a matter of, again, plugging in all of the numbers that we've got already identified, the masses and the distances. To save a little time, instead of plugging in all those values and writing all of them out, I'm going to put the answer here as 316.6 repeating grams. Again, I'm just simply taking object mass 1 and distance 1, plugging in mass 2 down here times distance 2 and D3 is our 30 centimeters up here. The final one is one that sets us up for something we're going to be doing in class with a lab tomorrow, where the pivot point now is off center. So what this does is essentially, it doesn't change how we measure the distances, but it changes the relative positions of the masses. So the two bullet points that you see over here, the meter stick is now what's actually on the right-hand side. There's not an extra mass hanging on that side. What we've got going on is one object hanging over here and no object over here. Because the pivot point is off center, the meter stick is actually what's being balanced. And we'll look at the specific numbers of this tomorrow so that you can see exactly how this works. But just recognize that this can indeed be done. At this point, if you are done with both the lab and watching through both videos of notes for today, you can begin working on the homework assignment for tonight, which is 4-4, until it is time to take the quiz during the last 15 minutes of the block today.